Sunspots are dark patches on the sun's surface, cooler than their surroundings and rich in magnetic activity. These fascinating solar phenomena play a significant role in shaping our understanding of stellar processes and their impact on Earth. Their existence reveals the interplay of heat, light, and magnetism in the sun's dynamic atmosphere. Sunspots are born in the sun's photosphere, a thin, luminous outer layer that radiates light into space. They appear darker because their temperature, around 3000 to 4500 K, is lower than the surrounding photosphere's 5800 K. The formation of these spots is tied to the sun's magnetic field, which experiences intense and localized disturbances. When magnetic field lines twist and break through the sun's surface, they create regions where convection, the process of heat rising and cooling sinking, is inhibited. These disruptions lower the local temperature, forming the dark regions we observe as sunspots. Often occurring in pairs or groups, sunspots can range in size from relatively small specks to enormous features larger than Earth. The life cycle of sunspots is intrinsically tied to the solar cycle, an approximately 11-year oscillation in solar activity. At the beginning of the cycle, called the solar minimum, sunspots are few and primarily appear near the sun's equator. As the cycle progresses towards solar maximum, the number of sunspots increases dramatically, and their positions shift toward higher latitudes. This periodic change reflects the sun's magnetic field reversing polarity, a process fueled by the internal rotation of plasma within the solar interior. Observing and counting sunspots is one of the key methods astronomers use to monitor and understand the solar cycle. Sunspots are not merely local phenomena but influence the entire heliosphere, the vast region of space dominated by the sun's influence. During periods of high sunspot activity, the sun often releases bursts of energy in the form of solar flares and coronal mass ejections, CMEs. These explosive events, powered by the magnetic fields associated with sunspots, eject massive amounts of charged particles and radiation into space. When these particles interact with Earth's magnetosphere, they can trigger geomagnetic storms, leading to breathtaking auroras but also potentially disrupting satellites, communication systems, and power grids. This connection between sunspots and space weather underscores their relevance to life on Earth. The study of sunspots has a storied history, from their first telescopic observations in the early 17th century by Galileo Galilei and other astronomers to modern-day solar missions like NASA's Solar Dynamics Observatory, SDO. Early observations challenged the notion of celestial perfection, revealing the sun as a dynamic and imperfect sphere. Today, advanced telescopes and spacecraft provide detailed imagery and data, allowing scientists to delve deeper into the underlying mechanisms of sunspots. By studying these enigmatic features, we not only gain insight into the behavior of our star but also improve our preparedness for the broader implications of solar activity on Earth and beyond.